When installing a 400 Hz distribution panel in an aircraft mock-up, it's important to use circuit breakers rated for 400 Hz. Using breakers not rated for the correct frequency can result in safety hazards and equipment damage. Circuit breakers specifically designed for 400 Hz will typically have the Hertz rating clearly marked on the device. Breakers designed for both 50/60 Hz and 400 Hz may have a Hertz rating range indicated. For example, 50/60-400 Hz. There are two main types of circuit breakers to consider: firstly, molded case circuit breakers, and secondly, air circuit breakers. Some molded case circuit breaker options include ABB SASA Max 2, available in ratings up to 1600 amps, 400 Hz, and Schneider Electric Master Pack 10W, also available in ratings up to 1600 amps, 400 Hz. Air circuit breaker options include GE Power System Versa Shield Plus, available in ratings up to 3000 amps, 400 Hz, and Siemens 3WL, available in ratings up to 6300 amps, 400 Hz. When selecting breakers, consider the specific requirements of the aircraft mock-up, including voltage, current, and fault current levels. It's also important to consult with a qualified electrician for proper installation and maintenance of the 400 Hz distribution panel. The selection and installation of 400 Hz circuit breakers requires a careful understanding of electrical principles and safety practices. Firstly, it is critical to understand the concept of frequency in alternating current, or AC, circuits. Frequency refers to the number of complete cycles of a waveform that occur in 1 second, measured in Hertz. In most residential and commercial applications, the standard frequency is either 50 or 60 Hz, depending on the region. However, certain specialized applications, such as those found in aircraft and some industrial settings, utilize 400 Hz power systems. The difference in frequency affects the behavior of electrical components, particularly inductive and capacitive elements. Secondly, circuit breakers are designed to protect electrical circuits from overcurrent conditions, such as overloads and short circuits. They achieve this by interrupting the flow of current when a predetermined threshold is exceeded. The design and characteristics of a circuit breaker are frequency dependent. Breakers intended for 50 or 60 Hz operation may not function correctly or safely at 400 Hz. This is because the impedance of inductive components within the breaker changes with frequency, affecting its tripping characteristics. Therefore, it is essential to use circuit breakers specifically rated for 400 Hz applications. Thirdly, identifying a 400 Hz rated circuit breaker typically involves looking for specific markings on the device. Manufacturers will clearly indicate the frequency rating, often with a label that reads 400 Hz or includes a range such as 50/60-400 Hz. This ensures that the breaker is suitable for use in both standard and high-frequency systems. If the frequency rating is not explicitly stated, it is crucial to contact the manufacturer or consult the product data sheet to verify its compatibility. Fourthly, the selection of appropriate circuit breakers requires careful consideration of several factors, including voltage rating, current rating, and interrupting capacity. The voltage rating must match the system voltage of the aircraft mock-up to prevent insulation breakdown and potential safety hazards. The current rating must be sufficient to handle the normal operating current of the circuit, with an adequate safety margin to prevent nuisance tripping. The interrupting capacity, measured in amps, indicates the maximum fault current that the breaker can safely interrupt without sustaining damage or creating an arc flash hazard. Fifthly, molded case circuit breakers, or MCCBs, are a common type of circuit breaker used in industrial and commercial applications. They are designed to provide reliable protection for electrical circuits with current ratings ranging from 15 amps to several thousand amps. MCCBs typically consist of a thermostating molded case, a set of contacts, a tripping mechanism, and arc extinguishing chambers. The tripping mechanism can be thermal, magnetic, or electronic, depending on the specific design and application. Sixthly, air circuit breakers, or ACPs, are another type of circuit breaker used in high current applications. They are similar to MCCBs but are generally larger and have higher interrupting capacities. ACB use air as the insulating medium to extinguish the arc that forms when the contacts separate during a fault condition. They are often used in main distribution panels and substations to protect critical electrical equipment. Seventhly, when installing a 400 Hz distribution panel in an aircraft mock-up, it is important to adhere to all applicable electrical codes and standards. These codes and standards provide detailed requirements for the design, installation, and maintenance of electrical systems to ensure safety and prevent hazards. In the United States, the National Electrical Code, or NEC, is the primary standard for electrical installations. Other relevant standards may include those published by the Institute of Electrical and Electronics Engineers, or IEE, and the International Electrotechnical Commission, or IEC. Eighthly, proper grounding is essential for the safe and reliable operation of any electrical system, including a 400 Hz distribution panel. Grounding provides a low impedance path for fault currents to return to the source, allowing the circuit breaker to quickly trip and clear the fault. The grounding system must be designed and installed in accordance with applicable codes and standards to ensure its effectiveness. Ninthly, regular maintenance and inspection are crucial for ensuring the continued reliability and safety of a 400 Hz distribution panel. This includes visually inspecting the circuit breakers for any signs of damage or deterioration, testing the tripping mechanism to verify its proper operation, and tightening all electrical connections to prevent overheating and loose connections. A qualified electrician should perform these maintenance tasks on a regular basis. Tenthly, consulting with a qualified electrician is highly recommended when working with 400 Hz power systems. Electricians have the knowledge, skills, and experience to properly design, install, and maintain these systems, ensuring their safe and reliable operation. They can also provide guidance on selecting the appropriate circuit breakers and other electrical components for the specific application. In addition to the technical considerations, there are also practical aspects to consider when installing a 400 Hz distribution panel in an aircraft mock-up. Firstly, the location of the distribution panel should be carefully chosen to minimize the length of cable runs and ensure easy access for maintenance. The panel should be mounted in a dry, well-ventilated area to prevent corrosion and overheating. Secondly, the wiring used in the 400 Hz system must be appropriately sized for the current carrying capacity and voltage drop requirements. The NEC provides tables and guidelines for determining the correct wire size based on the ampacity and length of the circuit. It is important to use high-quality wiring materials that are suitable for the operating environment. Thirdly, all electrical connections must be made using approved connectors and terminals. These connectors and terminals should be properly crimped or tightened to ensure secure and reliable connection. Loose or corroded connections can cause overheating and voltage drop, leading to equipment malfunction and potential fire hazards. Fourthly, the distribution panel should be clearly labeled to identify each circuit and its corresponding load. This helps to prevent accidental overloads and simplifies troubleshooting. The labels should be durable and resistant to fading or peeling. Fifthly, surge protection devices, or SPDs, should be installed to protect sensitive electronic equipment from voltage transients caused by lightning strikes or other electrical disturbances. SPD divert the surge current to ground, preventing it from damaging the connected equipment. Sixthly, proper coordination of circuit breakers is essential to ensure that only the affected circuit trips during a fault condition, minimizing downtime and preventing unnecessary interruptions. Coordination studies involve analyzing the time current characteristics of the circuit breakers to determine their optimal settings. Seventhly, the aircraft mock-up should be equipped with appropriate safety interlocks to prevent accidental contact with energized parts. These interlocks can be mechanical or electrical and should be designed to automatically energize the circuit when a door or panel is opened. Eighthly, personnel working on the 400 Hz system should be properly trained in electrical safety procedures and the use of personal protective equipment, or PPE. This includes wearing insulated gloves, safety glasses, and arc-rated clothing when working on or near energized equipment. Ninthly, a comprehensive set of documentation should be maintained for the 400 Hz system, including wiring diagrams, equipment specifications, and maintenance records. This documentation is essential for troubleshooting and future modifications. Tenthly, regular audits should be conducted to ensure that the 400 Hz system is operating safely and efficiently. These audits should be performed by a qualified electrical inspector and should include a review of the system documentation, a visual inspection of the equipment, and electrical testing. Additionally, it is important to understand the specific applications where 400 Hz power is commonly used. Firstly, aircraft utilize 400 Hz power systems for several reasons. The higher frequency allows for smaller and lighter transformers and inductors, which is crucial in aircraft design where weight and space are critical. Additionally, 400 Hz power reduces the size and weight of electrical motors used in various aircraft systems, such as pumps and fans. Secondly, some military and aerospace applications also utilize 400 Hz power due to its advantages in size, weight, and efficiency. These applications may include ground support equipment, radar systems, and communication equipment. Thirdly, certain industrial applications, such as those involving high-speed machinery or precision control systems, may benefit from the use of 400 Hz power. The higher frequency can improve the performance and efficiency of these systems. Fourthly, research and development laboratories may also use 400 Hz power for specific experiment or testing purposes. This allows them to simulate real-world conditions found in aircraft or other specialized applications. Fifthly, when working with 400 Hz power, it is important to be aware of the potential hazards associated with high-frequency electricity. These hazards include increased skin effect, which can cause current to flow primarily on the surface of conductors, and increased electromagnetic interference, or EMI, which can disrupt sensitive electronic equipment. Sixthly, to mitigate the effects of skin effect, it is important to use conductors with a larger surface area, such as stranded wire or bus bars. This helps to distribute the current more evenly and reduce the risk of overheating. Seventhly, to minimize EMI, it is important to use shielded cables and enclosures and to properly ground all electrical equipment. This helps to contain the electromagnetic fields and prevent them from interfering with other electronic devices. Eighthly, special test equipment may be required to troubleshoot and maintain 400 Hz power systems. This equipment includes frequency counters, oscilloscopes, and harmonic analyzers. Ninthly, it is important to use qualified personnel who are familiar with 400 Hz power systems to perform any maintenance or repairs. These personnel should have the necessary training and experience to safely work with high-frequency electricity. Tenthly, always follow the manufacturer's recommendations and safety guidelines when working with 400 Hz power systems. This includes using the correct tools and equipment, wearing appropriate PPE, and following proper lockout/tagout procedures. Finally, remember that electrical safety is paramount when working with any electrical system, including 400 Hz power systems. Always take the necessary precautions to protect yourself and others from electrical hazards. In addition to the above points, it's crucial to consider the long-term reliability and maintainability of the 400 Hz distribution panel. Firstly, selecting high-quality components from reputable manufacturers is essential for ensuring the longevity of the system. This includes not only the circuit breakers but also the wiring, connectors, and other electrical components. Secondly, implementing a preventive maintenance program can help to identify and address potential problems before they lead to equipment failure. This program should include regular inspections, testing, and cleaning of the distribution panel and its components. Thirdly, keeping spare parts on hand can minimize downtime in the event of a component failure. This is particularly important for critical components such as circuit breakers and transformers. Fourthly, providing adequate ventilation for the distribution panel can help to prevent overheating and extend the life of the components. Overheating can cause premature failure of electrical components and increase the risk of fire. Fifthly, protecting the distribution panel from moisture and corrosion can help to prevent damage and maintain its reliability. This may involve using a weatherproof enclosure or applying a protective coating to the components. Sixthly, regularly calibrating and testing the circuit breakers can ensure that they are operating within the specified parameters and providing adequate protection. This is particularly important for electronic trip circuit breakers, which may drift over time. Seventhly, keeping accurate records of all maintenance and repairs can help to track the performance of the distribution panel and identify any recurring problems. These records should include the date of the maintenance, the work performed, and the parts replaced. Eighthly, providing training for personnel on the proper operation and maintenance of the distribution panel can help to prevent misuse and ensure its longevity. This training should cover topics such as safety procedures, troubleshooting techniques, and preventive maintenance tasks. Ninthly, considering the environmental impact of the distribution panel and its components can help to reduce its overall footprint. This may involve using energy-efficient components, recycling materials, and properly disposing of waste products. Tenthly, staying up to date on the latest technologies and best practices in electrical distribution can help to improve the performance and reliability of the 400 Hertz system. This may involve attending industry conferences, reading technical publications, and consulting with experts. In conclusion, installing a 400 Hz distribution panel in an aircraft mockup requires careful planning, attention to detail, and adherence to all applicable codes and standards. By following these guidelines, you can ensure the safe, reliable, and efficient operation of the system. Remember to always consult with a qualified electrician for assistance with any electrical work.